Hey, welcome back to 15-Minute Math. Last episode we did finding limits analytically, particularly with continuous functions. And we went through a lot of theory. We didn't go through a lot of examples, so I thought maybe it would be good to just do a few examples, work out a few problems. I know examples sometimes really clarify things. Theory is nice, but examples are nice too. So this video is going to be mostly examples, and there's not going to be a lot of theory, just kind of working some problems. But I do want to maybe remind us, remember the whole point of last video was if you have a limit that you need to evaluate, and the limit is continuous, the function is continuous, the function that we're trying to find the limit of is continuous at the point we're trying to find the limit, then we can just plug that point in. But probably the hardest thing for at least beginning students is, well, how do I know if that function is continuous or not? And so maybe we should make a list of the types of functions that are always continuous. And these functions are, well, of course, linear functions. And in fact, maybe I'm just going to put polynomials. Of course, we know linear functions are polynomials. But I just think most of the time when we think about polynomials, we think higher order polynomials, quadratics, cubics, quartics, those things. Maybe we should put functions here, linear functions. Exponentials are always continuous. Okay. Cubic functions. Oh, I'm sorry, not cubic. Cubic functions are continuous, but they're polynomials. I meant that in my head I was thinking cube root functions. So cube root functions. Maybe I should just say odd root functions, right? Because fifth roots, seventh roots, those are all. Okay. What else would be good to include on our list here? I don't know, that might be about it. Let's look at some trouble functions. What functions are going to get us in trouble? We saw on our last video, piecewise functions are not always going to work out so well. Not to say they'll never work, but they can definitely get us in trouble. Rational functions. Can't divide by zero. Rational functions are prime examples of trouble functions. What else can throw off continuity? But what about square root functions? Can't have a negative under a radical. Well, not an even radical anyway. Kind of like we did before. Maybe I'll just in parentheses, even root. Of course, the square root's probably the most popular, but there's, you might see a fourth root, sixth root, something like that. Oh, logarithms. Can't take a logarithm with a negative or zero argument. So those could be trouble functions. So, if I'm looking at anything on my left column, almost always I could just plug that thing in and get an answer. My answer is my limit. If I'm on the right, I might have to be more careful. Maybe I should check out the graph. Maybe kind of explore that function a little bit further before I just go and blindly start plugging things in. Now, we'll see in a couple examples here why sometimes just plugging it in and seeing what happens is not a bad strategy. But let's look at an example here. So let's find the limit as x goes to 4 of 1/2 x squared plus 5x minus 7. And if I'm doing this limit, I'm the student here, and I have to do this as a homework problem or a quiz or whatever, I'm thinking to myself, is this a trouble function? And it's not. I mean, it's a polynomial. So I'm pretty certain that I can just plug this in, and so let's try it. Maybe over here I'll just do some scratch work. 1/2 of 4 squared plus 5 times 4 minus 7. Well, 4 squared is 16. Half of that is 8. That'd be 8 plus 20, so it's looking like this limit is 21. Now, here's the kicker. If you can get an answer by plugging it in, that's your answer. Like, I can't think of a scenario in which you can plug a function or plug a number into the function and get a sensible answer, and then that be the wrong answer. If you can find a function value, that is your answer. I guess the one exception would be piecewise functions. We saw that in our last video, where the function value was one thing, but the limit didn't really exist. So I guess piecewise functions are the exception to that rule, but if it's not a piecewise function, It's what, quote unquote, a normal function. Then if you can get an answer, generally that is your answer. And so what I mean by that is here, let's say we had the limit as x goes to 3. And let's say it was going to be x squared minus 6x plus 9 over x squared minus 9. And so again, maybe it's worth our while to think, is this a nice function or is this a trouble function? Well, this is a rational function. That's a trouble function. So I should be, a little bit weary right off the bat. And so again, let's maybe do some scratch work. 3 squared minus 6 times 3 plus 9 over 3 squared minus 9. And you can probably see the issue here. I'm going to get 9 minus 18 plus 9 over 9 minus 9. I'm going to get 0 over 0. That's an indeterminate form. We really can't gather much information about that. And so we really can't do the limit analytically. I don't know. We could probably go over to Desmos and look at a graph to get the limit, or at least estimate the limit, but we can't do it analytically, not by plugging it in. Maybe there's going to be a different method down the way, but right now we're kind of up the creek. Now, notice that this does not necessarily mean the limit doesn't exist. There might be a limit as x goes to 3 for this function. We just don't know what it is. Like 0 over 0 doesn't give us much information about what that limit would be. We need different methods to do that. Now, one thing I do want to draw your attention to before we leave this function, and actually I was going to rewrite it, but I'm realizing that's a waste of space. So let's say we had that very same function, which remember, this could be a trouble function, but instead of evaluating the limit at 3, maybe we want to evaluate the limit at, I don't know, 5. Let's do 5. And let's see here. Well, in my head, I'm thinking, uh-oh, this is a trouble function. This may not work out so well. But let's see. It's always worth a shot. Plugging values in is like our first resort. Like that's the first. That should be our go-to. So, even if in the back of your head you're like, this may not work out, it's at least worth a shot to plug it in. See if you get something sensible. Let's see here. What is this going to be? 25 minus 30 is negative 5 plus 9 would give me 4. And that would give me, is that 16? I want to say that's 16. Okay, so I get 1/4. Oh, well, look, I got a sensible answer. So that limits 1/4. So just because your function is on the list of trouble functions, don't necessarily throw it out. You could still plug it in, because remember, the only trouble spots are where that function is discontinuous. And rational functions are continuous almost everywhere. They usually just have 1 or 2 points of discontinuity. They're asymptotes or maybe a hole or something like that. And in fact, I think it is going to be worth our while to go over and look at the Desmos graph of this to see why 5 worked, but 3 was kind of nonsensical. So here's our graph. And you can see as we get towards 3, there's a hole in the graph. There's a hole. And so and you saw what happens whenever you try to plug in 3, you get 0 over 0. And so that's why plugging 3 in did not work. There was a hole right at 3. But there's not anything goofy at 5. I mean, you could find the limit at 5, no problem. And so you can see from this graph that this thing has a hole at 3, and it looks like it's got a vertical asymptote at negative 3, which, if you remember from your pre-cal days, that shouldn't be a surprise, because if I factor the denominator, that's a difference of 2 squares. It's going to be x plus 3, x minus 3. And so I should, get some discontinuities at 3 and negative 3. It just so happens this was a point discontinuity. So it was only discontinuous at a single point, and this was an asymptote. So these are trouble functions, but, outside of those areas of discontinuity, they're actually not too bad. I mean, obviously you have to deal with fractions, so maybe they're not as great as polynomials, but you can still get sensible answers as long as you're not at one of those discontinuities. Okay, so our plug-in method really is powerful because other than very, few instances, most of the functions we deal with, at least at Calculus 1, are pretty well behaved in that they're continuous almost everywhere. There's usually only just a couple points where they're discontinuous. Okay? And so, let's try another example. All right, let's say I take the limit as maybe x goes towards 3 of the cube root of x squared minus 1. And okay, so this looks like a complicated function. This might get nasty, but let's think about it. It's an odd root function. It's a cube root function, right? Those things are pretty well behaved. I don't see any reason that this would be discontinuous anywhere. We could probably just plug this in, and let's see what happens if we do. So that's going to be 3 squared minus 1. Well, that's the cube root of 9 minus 1, which is the cube root of 8, which luckily is not that bad to evaluate. That is just 2. So that limit is 2. And, if you're questioning, hey, does this work or not? Oh, jump over to Desmos, graph it. If the graph matches what your analytical method is saying, then, I'm sure you've done it right then. But really, the moral of the story is, aside from piecewise functions, if you can get an answer just from plugging it in, then, that is your answer. So always your go-to should be plug it in. If you plug it in and then you get a weird answer, like we did over here when we tried to plug in 3, okay, then we're going to have to think about other methods, or there's the possibility that the limit just straight up does not exist. Okay, so I got one more example, and you can see it on the screen here. So consider g of x to be this piecewise function. So it's going to be this square root function for x less than equal to 0, and then it's going to be that linear function if x is bigger than 0. And we're going to evaluate these 3 limits, but before we do that, well, I tell you what, we're going to hold off. Let's evaluate a and b, and then we'll talk about c. So if I want to evaluate the limit as x goes to -4, so I'm going to use that top rule, right? -4 is less than 0. So I'm just going to plug this in. I'll have, I'll just do some scratch work down here. I'll have -4, take the square root. And so, of course, that's just going to be the square root of 4, so 2. All right, I could plug it in, no problem. What about this one? So 2. 2 is bigger than 0. So I'm going to be using this rule here. So it's just going to be 2 times 2 plus 1. So far, plugging things in has worked out swimmingly. Now, this one right here is going to give us fits. The limit is x goes to 0. Well, 0 is equal to 0, so we're going to use the top rule. So we're going to find the square root of -0, which is just 0. So the plug-in method suggests this should be 0. However, that's not right. That is not the limit. And in order to understand why that's the case, we need to think about the graph of this function. Specifically, what happens to it right around 0. So at 0, this thing is a square root function that's been reflected over the y-axis. It's going to look something like that. And then if x is bigger than 0, it is a linear function with a y-intercept of 1 and a slope of 2. It's going to look something like that. And so you can see I have a jump discontinuity right at 0. So if I approach from the left, yeah, certainly it looks like the limit's going towards 0. But if I approach towards the right, now the limit's going to be 1. So actually this limit does not exist. And so we have to be careful about that. Remember I said that piecewise functions, really, you have to be careful with the plug-in method because there exist scenarios where you could plug in your value, get an answer, think everything's peachy, but if it's got one of these jump discontinuities, then you're still going to be missing something. So for piecewise functions, really, especially at the breaks, if you're evaluating limits at the breaks of the piecewise functions, be very, very careful that there's not a jump discontinuity there, or else your plug-in method may give you the wrong answer. All right? But other than that, the plug-in method, if it does work, that should give you the right answer.